We're going to have a new definition. It's a vector space, okay? It's isomorphic to Rn, so it looks like Rn. Now we have a new definition, which is the tangent bundle. So this is what? Set of all attainable velocities at all P in M. So combine all of them together. With the following caveat. We have this guy, this is the tangent space here, this is the tangent space there. Yes, please collect all of them. So with the following caveat, please don't tell me that I here cover the xy velocities, here cover the xz velocities. So when I combine all these velocities, it means that the tangent bundle is the three-dimensional velocities. I can go anywhere. I have the capability to generate all velocities. No, this is incorrect. This is not correct. Okay? Why? Because yes, you have capability to generate xy at this point, not at that point. You have a capability to generate xz velocities at this point, not at that point. So this is why the tangent bundle, which we denoted by TM, it's not at a particular point because we collect all the points now. It's the union over P of TPM, but this is not any union, it's actually disjoint union. And I will talk about that now. Disjoint union. Just reminding you, on a side, if you have two sets, 1, 2, 3, and maybe 5 and 7. What is the union? The regular union. That's okay. It's just a collection of all things. If you have repetition, just remove the repetition. And what is A? Disjoint B. Collect all the elements but keeping your identity. Where did you come from? 1 coming from A, 2 coming from A, 3 coming from A, 5 coming from B, and 7 coming from B. Some people write it actually as pairing. So 1 and 0, 2 and 0, 3 and 0, 5 and 1, 7 and 1. With the second entry, the label of the second entry labels where do you come from, 0 for A and 1 for B, okay? Did you get this? Mm-hmm. So just collect all the elements, but keep your identity. That's it. This is the message. And this is precisely what we need to have here. Yes, we need to collect all the velocities, keeping our identity. This velocity was attainable at that particular point, okay? So this is why it's disjoint union. Any question about that? So simply without any, sophistication, it's simply the set of all P and V such that P in the manifold and V where?
Tangent space at P.
Very good, TPM, right? That's it.
So I have a question.
Yeah.
If in set B we have 2, so it's 2, 5, 7.
It would be a new element.
Oh,
right? Because
so
it's technically
two, one,
it will be 2, 1 is
oh,
different from
okay.
2, 0. Very good question. Okay? Yeah, it's a new element. Any question? Okay. So it's nothing fancy. If the manifold has the set of points, positions, and the tangent space has the set of velocities at this point, then the tangent bundle has the set of positions and velocities. It's your state space. So in mechanics, we have positions, q's, and we have q dots. So the space that has both q and q dots, this is our tangent bundle. So it's actually really very related to mechanics. In configuration manifold, this is a manifold. Then this is the set of all q's, right? Then we have the tangent bundle, TQ or TM, is the set of all q and q dot, right? So this is the state space. We have a configuration, and this is the state space, which is positions and velocities in mechanics. So for example, for the pendulum, for example, this is theta, which we know very well that it lives in S1, right? And at any point in S1, at any point, it has velocities. It can go this direction, go that direction, and there is no limit actually on the velocity. So this is R. So at any point in S1, we have attainable velocities R. So TS1 in particular, TS1 is simply S1 cross R. So you have something like, at this point I can go all the way up and down, I can go all the way up and down. So it looks like a cylinder, right? So the configuration here is a circle, and the tangent bundle, which is the state space, is the cylinder. Any question about that? In general, Tm, in general, not necessarily equal to
Professor?
M across Rn. Yes, please.
What the real number that the R represents?
Velocities, right? At this point, you can have velocities, any positive or negative number. Because we're collecting positions and velocities now. Okay, in general, Tm is not just a product. It is more complicated than a product. Particularly for S1, it's a product. But for example, for S2, it's not a product. And this has a very interesting story, but we don't have time to can talk about it offline. But actually, locally, yes, it's a product, if you are interested in this thing. So locally, for any U in M open, TU, remember U is actually a manifold. Why? Because any open subset of a manifold is a manifold itself. TU is isomorphic to U cross Rn. Okay? So locally it's like a product, but globally it's not a product. So I'm just giving you this statement. It's a subtle issue, so don't expect that it's always a product.
It doesn't have to do with if the manifold drops dimension or not?
No, it has to do with the existence of a vanishing vector field everywhere. I mean, we can talk about it. No, it's not drop dimension. So like S2, for example. S2 is, you cannot write it as product, globally. Okay, so we covered the tangent bundle, very good. Actually, the tangent bundle, yeah, you can see it's set of positions and velocities, the state space for a mechanical system, but mathematically, we invented it actually to provide the domain and range for tangent map, push forwards and tangent map. Why? Because think about it. So here is M, here is N, here is F. F is a map from M to N. When you say F star is a map from where to where? At a point, it maps TPN to TF of PN. But globally, what is the domain? So far, we didn't have an entity, and we just defined an entity that is TM to TN globally, right? So actually, this is the mathematical objective of the tangent bundle, to provide domain and range for tangent maps. Any question about that? Very good. Actually, we have 5 minutes. We can talk about vector fields. Any questions so far before going to vector fields? Feel free to come up with questions, please.
Professor, the bundle for the tangent bundle actually, I guess they are not free because the set of all velocities is restricted by the problem, by the mechanical problem itself.
That's okay. So it's a very good point, but it's a subtle issue here. In the sense, if there are no further constraints, once you define the manifold, the set of all velocities are defined by the tangent space. There are no further constraints. So they are free in that sense. If you just look at the manifold, don't look at the ambient space. Obviously in the ambient space they are not free. Why? Because I'm always not able to go normal to the surface. So in the S2 three-dimensional, I always cannot go normal to the surface. So there is always missing one direction that I cannot go at any point. But we're not talking about that. Actually, intentionally, right? So we work on the manifold. But later on in mechanics, you can add non-holonomic constraints. So then we will add further constraints to the geometry of the shape. Okay? Okay, so vector fields. It's a very natural notion. Vector field V takes a point P in M and gives you a velocity vector in TPM. That's it. So at any point it gives you a vector. At this point it gives you an arrow for a vector, like a velocity field for flow around any object or something. At any point you have an arrow. 3 components. So it looks like a vector valued function. Looks like a vector valued function on Rn, if we're talking about Euclidean space, like V is equal to x, y, x squared plus y squared. This is a vector field on Rn, on R3, right? At any point, we'll give you a 3-dimensional arrow. Like V is x or y, negative x and 0. This is on S2, the example that we had in mechanics. So this is the thing, this is your vector flying westwards. This is that vector field. Okay? So at any point on the sphere, it gives you a vector that is tangent to the sphere. Okay? So, because I will use this a lot, the set of all vector fields on M, I will denote it by some symbol, right? Sometimes we call them gamma, but I realize it will confuse with Christoffel symbols later. So let's use this guy. Some books use this guy, chi. So, okay. Set of all vector fields, chi on M. Okay. So, so a vector field on a manifold is a map, right? That takes a point and gives you a vector in the tangent space. So it's a map from the manifold, right? To what? T.
The tangent space. Yeah.
Tangent space. If a point, I'll say the tangent space at the point, but
Tangent
globally, so this is the tangent bundle, right? So technically, the vector field takes a point and gives you a 2n components, right? But the first n are trivial because it's the location of the point, I know it anywhere. So we focus on the last n, okay? So, the vector field at this point gives me a vector, at this point gives me a vector, at this point gives me a vector, but you just said that any vector is just the velocity vector of some curve. Any vector is the velocity vector of some curve, any vector is the velocity vector of some curve. So if we connect this, we will get a curve, right? And this curve has a name, of course, it's the integral curve of V at P. Okay, so if you integrate V is the velocity. If you integrate the velocity, you get a curve. This is the integral curve. I guess we'll continue next time from here. So integral curves.
How we can show P in the picture?
You start somewhere.
Oh, okay.
Say start from this point. Yeah, thank you. Okay, guys. There is a homework that is due next lecture. Okay, next lecture. And also there's another lecture that you need to watch to solve the thing. Sorry about that.